Welcome back to the deep dive. This is where we take your sources, add a dose of curiosity, and really dig out the most valuable insights.
That's the plan.
Today we're exploring, well, it sounds like a pretty technical corner of science, simulating atoms and molecules.
Right, how they behave.
But it's actually, I think, a really fascinating story. It's about clever compromises, intense competition, and finding the right tool for the right job.
And the source material for this dive is a paper by Jonathan E. Musa. It's called The Enduring Relevance of Semiempirical Quantum Mechanics.
Okay.
And it really tells the story of the simulation approach. It used to be huge, then things shifted dramatically. But it still have, lessons for us today. Potential even.
So our mission today then is to unpack this. Understand what semi-empirical quantum mechanics, let's call it SQM.
SQM, yeah.
What it actually is. Figure out why it sort of, lost ground over the past few decades. And maybe most importantly, why it could still be surprisingly relevant to you, depending on the kinds of scientific puzzles you're trying to crack.
Exactly. There's this, polarization happening in the field.
Polarization.
Yeah, and SQM is kind of stuck right in the middle. We want to figure out why and what that really means.
Okay, let's dive in then. Atomistic simulation. The goal is understanding things like materials, biological systems.
By figuring out what the atoms and electrons are up to?
Yeah. And the most accurate way to describe these tiny things is quantum mechanics, QM.
Right. The gold standard, in theory.
But QM calculations, especially if you have lots of atoms, they're just incredibly expensive, computationally speaking.
Hugely expensive. And even back in the day, scientists wanted to run these simulations way before computers could really handle the full QM equations easily.
So necessity was the mother of invention here. They needed a shortcut.
Precisely. Yeah. Scientists look for ways to build simpler approximate versions of those really complex QM calculations. They'd often simplify bits of the math, and then they'd, tune some parameters like adjustable knobs, basically to make the results match experiments.
I see.
And that's where these SQM methods came from. Different flavors popped up, some from quantum chemistry, like the AM1 model, which is pretty well known.
Right.
Others more from physics. But the shared goal was always speed. How do we approximate QM efficiently?
So SQM got popular because it offered that balance between the ideal QM and what you could actually compute back then.
Exactly. The source paper really emphasizes that. In the early days, SQM methods held a really significant piece of the, let's call it the atomistic simulation market.
Market share, yeah.
They were the go-to for a lot of problems. But things have changed a lot, especially over the last 30 years or so. The field got really polarized.
Polarized. How does that look in, scientific software? What does that mean?
It means development and maybe more importantly, usage has really drifted towards two extremes.
Okay, what are the extremes?
Well, on one side, you've got the push for ultimate accuracy, usually for smaller systems or maybe just a critical part of a bigger system.
Right.
And this is dominated by general purpose, high accuracy ab initio QM methods.
Ab initio from the beginning?
Pretty much, yeah.
Yeah.
Aiming to solve things from first principles, minimal experimental fiddling. And thanks to faster computers, methods like DFT density functional theory, they've just exploded in popularity there.
Okay, so that's the accuracy extreme. What's the other pole?
It's all about speed. Raw speed for massive systems.
Like millions of atoms.
Yeah, think simulating a whole protein folding up in water or huge material structures.
Yeah.
For that, you need really fast methods, often called molecular mechanics or MM.
Yeah.
These use much simpler models, kind of physics-inspired, like springs connecting atoms. Super, super efficient, but less accurate for the fine chemical details.
It's a cost difference.
Oh, it's huge. The paper points this out starkly. Calculating the forces on atoms, which you need constantly in simulations, can be 1,000 times faster with MM than with QM.
Wow. 1,000 times.
Yeah. And SQM sits, somewhere uncomfortably in between those two.
Okay, yeah, that really puts SQM in the middle, doesn't it? Speed, cost, accuracy. So with QM getting better and MM getting faster, what happened to SQM's piece of the action?
It shrank dramatically.
How dramatic?
The paper actually cites evidence. Looking at academic software citations, it collapsed from maybe over 20% back in the 90s to only around 1% today.
1%, wow.
Yeah, that relentless drive towards either absolute accuracy with QM or absolute efficiency with MM, it just squeezed SQM out.
So the big simulation packages people use now?
They're overwhelmingly either QM powerhouses or MM workhorses, the dedicated SQM programs. They just don't have that same broad user base anymore.
Okay, so we can see how SQM got caught in that squeeze, lost its market share. But the paper's title argues for its enduring relevance. So where does that come from? Where's the comeback potential or the continued value?
Right, and that's where it gets really interesting. It's not just, nostalgia.
Huh.
It comes from some pretty concrete lessons SQM's history can offer to modern QM.
Okay.
Lessons QM's success can teach SQM for its future.
Ah!
And also the potential for SQM to actually play a key role in new areas, especially with machine learning becoming so big.
Okay, let's unpack those. What wisdom can SQM pass on to QM? What are the lessons?
Well, because those early SQM developers were forced to work with limited computing power, right?
Yeah, the constraints.
They became masters of trade-offs.
Yeah.
They really had to figure out how to budget their computational cost and also the potential error across different parts of the calculation.
Different parts.
Like the initial description of the system, the Hamiltonian, they call it how you actually calculate the total energy and the numerical methods you use to solve the equations.
Okay.
This deep thinking about cost and error budgeting, that's something even cutting-edge QM methods, with all their power, can still benefit from today.
That makes a lot of sense. Constraints force you to be smart about where you put your effort. Okay, so how about the other way? What can QM teach SQM?
Modern QM software has gotten really sophisticated. It's often very modular.
Modular, like Lego bricks.
Exactly, yeah. Built from interchangeable components.
Uh-huh.
It also uses standardized ways of describing things like how to represent the atomic orbitals or different approximations.
Right. Standard libraries and formats.
Yes. And the paper argues that future SQM models could be built by essentially picking and choosing reliable components like libraries for calculating tricky integrals or solving equations that were originally developed for QM.
So the idea is SQM's future might involve kind of scavenging the best bits from mature QM software.
That's a good way to put it, leveraging decades of QM software engineering. But there's a challenge there.
Oh.
The efficiency of the traditional SQM methods often came from very specific, low-cost approximations built right into their core.
Like cutting corners in specific ways.
Sort of, yeah.
Yeah.
For instance, some methods just ignored certain complex electron interactions. The MNDO approximation is one example. Made them fast, but also introduced errors. QM components, though, they're built for accuracy. They might not have those specific speed hacks built in. So if you use QM parts, the SQM developers need to be really clever about where the efficiency gains are going to come from in the new SQM model.
This brings up a really important question then. How do you even figure out the best way to build or improve these SQM models, whether they're old or new? It sounds like a really complex balancing act, all these compromises.
It absolutely is. Historically, SQM development could be a bit monolithic. You kind of develop the whole model as one big thing.
Right.
The paper really pushes for deconstructing the model.
Right.
Breaking it down into those components we mentioned, Hamiltonian, energy model, solver, and analyzing the error and the cost from each part.
Okay.
Because just trying to slap a really sophisticated, accurate method for one part onto a simple old SQM model for another part, that often didn't work out so well. The errors didn't cancel nicely,
Yeah, you need balance.
You need balance across all the components.
And what about tuning those adjustable knobs you mentioned, the parameters? How do you do that effectively?
Well, traditionally, it was often a bit of trial and error. Or using fairly simple fitting methods, trying to match experimental data, or maybe results from highly accurate QM calculations.
Right.
The source suggests that applying modern statistics and model selection techniques can make this much more robust.
How so?
It can give a precise statistical meaning to choosing the model and the parameters that are most likely to succeed at a specific simulation task.
Specific simulation task. That sounds like a really key phrase here.
It really is. This idea of task distributions is fascinating. Think about, are you trying to simulate, say, a molecule's exact shape?
Okay.
Or maybe how strongly two molecules stick together, or the energy released in a chemical reaction. These are all different tasks.
Right. Different questions you're asking.
Exactly. And understanding the common tasks that scientists actually use atomistic simulation for can guide how you fit those SQM parameters.
So if you tune a model to be good at predicting how molecules interact,
it'll likely perform better at predicting, say, stable molecular shapes than if you tuned it solely to predict the energy needed to break bonds, like heats of formation.
So the insight is you tailor the method specifically for the job at hand.
Precisely. Like tuning a car engine differently for drag racing versus highway cruising, and this focus on specific tasks also opens the door for clearer comparisons.
Comparisons between different methods?
Yeah. Ranking methods in software based on their cost and their accuracy for those particular jobs. It helps users navigate the, frankly, dizzying array of options out there.
You mentioned machine learning earlier, too. How does ML fit into this evolving picture of SQM?
Right, ML. It's a major area where SQM research is really active now.
Mm-hmm.
And ML is being used in a couple of main ways.
Okay.
One is using ML almost like a correction layer. You run your SQM calculation, and then you use an ML model on top to refine the energy prediction, creating these hybrid ML-SQM methods.
Okay, like a finishing touch. And the other way?
Integrating ML machinery directly into the SQM model itself.
How'd that work?
Well, for instance, you could use ML to make the parameters depend on the local environment, so they adjust based on what atoms are nearby.
Ah, adaptive parameters.
Exactly. Or using ML to improve the whole parameter fitting process itself, making it smarter, faster.
So ML is both kind of enhancing the existing SQM and potentially being built right into the foundation of new ones.
Yes, absolutely. ML adds tremendous flexibility. It lets SQM models potentially capture more complex behavior, fit to a wider range of data, theoretically boosting accuracy.
But there's always a but, isn't there?
Yeah, usually. Yeah, the paper points out some important caveats. Older, simpler SQM models achieved broad applicability. They worked for many elements using relatively simple rules.
Okay.
ML models, though, especially as you try to cover more and more elements across the periodic table, they can face this challenge of a combinatorial explosion of parameters. You just need vastly more training data.
Right, the data requirements balloon.
Exactly. And also, while ML components are often thought of as computationally cheap, their costs can add up.
Right.
If they get too complex, they can actually end up costing more than the underlying SQM calculation they're supposed to be helping.
Negating the whole efficiency benefit.
Potentially, yeah. You could lose the speed advantage you wanted from SQM in the first place.
So it sounds like ML adds a lot of power, but also introduces new trade-offs, new complexities you have to manage.
Precisely. It's always that cost versus benefit analysis.
Mm-hmm.
Let's maybe look at a concrete example the paper uses.
Yeah.
Pretty simple.
Okay, yeah.
A minimal SQM model designed just for hydrogen atoms, forming little clusters like H2, H3.
Just hydrogen, okay.
So even when they isolated the error, just in the basic description of the electrons, the Hamiltonian part, this carefully tuned minimal SQM model actually performed better than a standard minimal ab initio QM calculation for predicting the energies of these little clusters.
Really? The simple SQM beat the basic QM. That's surprising.
It did, for that very specific, very limited system and task. But, and here's the other side, the example also showed the limitations.
How so?
A more flexible QM approach, one using a larger, more detailed basis set, think of it like using a higher resolution picture for the electrons,
Right.
did outperform the minimal SQM model, especially in regions where chemical bonds were forming. So it shows that just tuning a minimal SQM isn't some magic bullet. It can't necessarily match the accuracy potential of more sophisticated QM, even if it can beat basic QM for certain specific problems.
So even in that really simple case, the trade-offs are super clear. SQM can be really effective when it's hyper-focused on a specific task, maybe even beat basic QM.
Right.
But as soon as you demand higher accuracy or you need to scale up, you're quickly pushed back towards more complex and usually more expensive QM methods.
Exactly right. And that hydrogen example also suggested maybe a strategy for building SQM models for heavier elements.
Oh, yeah. What's that?
Maybe fit the parameters element by element, or for pairs of elements, using really accurate data just for small clusters involving those specific elements.
So break the big problem down.
Yeah, break down this huge, complex fitting problem into smaller, more manageable pieces, like solving a giant jigsaw puzzle by doing the corners and edges first.
Wow, okay. That was quite the journey through this whole landscape of atomistic simulation methods.
It really is a landscape, isn't it?
Yeah. We've seen SQM, its ingenious start as this necessary shortcut, then the tough competition, the decline against QM's accuracy and MM's speed.
But squeezed hard.
But also these compelling arguments for why it might still be relevant. Drawing lessons from its own past, looking towards a future maybe with more modularity, maybe enhanced by machine learning.
Absolutely. The paper really makes you think about this whole thing as a kind of market for scientific methods, doesn't it?
Yeah.
Where there's supply and demand for different levels of accuracy, cost, capability. SQM's market share decline is, well, it's a fact. But the arguments for its continued importance, they're quite strong, whether you look at it pragmatically, like what solves my problem, or even more idealistically.
And it really seems like understanding those actual task distributions, what people really use these simulations for, that's becoming more and more critical.
For sure.
It doesn't just help tune methods like SQM, but it helps scientists figure out where the gaps are, where new methods might be needed across the whole spectrum.
And that vision of building methods from standardized modular parts, maybe even bridging the QMS-QMM divide somehow, that could be really key to filling those gaps.
Right.
That simple hydrogen example, it showed that even a basic SQM approach, if you carefully design and parameterize it for a very specific task, it can carve out its own useful niche, even with its fundamental limits compared to the fancier methods.
So here's something maybe for you, the listener, to ponder. This world of atomistic simulation, it seems to be pulling towards extremes, right? Ultra-high accuracy on one end, maybe even quantum computing down the line.
The ultimate QM, yeah.
And then ultra-efficiency on the other, leaning heavily on machine learning and MM.
Speed above all else.
So the question is there still an essential need for a robust, flexible, well-understood middle ground, like semi-empirical quantum mechanics? Or is it kind of destined to be mostly a historical footnote, or maybe just used in very specialized niches?
Think about the problems you might need to solve. Do they absolutely demand the highest possible accuracy, no matter the computational cost?
Or are they huge simulations where speed is just paramount? You have to get an answer, even if it's less precise.
Or is there maybe a sweet spot, a place where a method like SQM, striking that balance between cost and accuracy, could actually be the ideal tool, especially if, as the paper suggests, these methods become easier to adapt, more modular, easier to parameterize for the specific tasks you care about.
Well, that's it for this deep dive. We really hope this look into semi-empirical quantum mechanics has given you a clearer picture of its past, its present, and maybe its potential future place in the whole scientific landscape.